electron affinity is kind of the opposite of ionization energy. So this isn't losing an electron, it's gaining an electron. And we don't say it's the energy cost, we say it's the energy change when a neutral atom becomes an anion, when it gains an electron. Electron affinity is usually negative, exothermic. So now you're giving the atom an electron, you don't pay it to take that, it pays you. You're giving it something, right? And so these are often negative, exothermic. There are some that are positive, and these are alkaline earth metals and noble gases. So why would a noble gas have to be paid to take an extra electron? It already has the ideal electron configuration. It's got 8 valence electrons. It's set. You're asking it to take one more and mess everything up, right? Well, you're going to have to pay me to do that. Whereas something like fluorine, fluorine's really excited to get another electron because now it's going to look like a noble gas, right? And these alkaline earth metals as well, when you give them an electron, now you're getting them farther away from what they want to become. The trends here are not as regular. Electron affinity does decrease, meaning it becomes more positive as you go down group 1A, but the other groups don't show a trend. Generally increases as you go across, becomes more negative. But again, there's a lot of exceptions. The highest electron affinity in any period is the halogen. So this makes sense because, fluorine, chlorine, bromine, iodine, those are the halogens. They want to gain an electron, right? Because that'll give them a noble gas electron configuration. So that's going to be the largest negative number, meaning they're going to pay you to give them an electron. Whereas some of the other ones, you have to pay them to take the electron from you. Yeah, that's it. Okay, metals and nonmetals. So if we learn the properties of metals, then the nonmetals are kind of like not, right? They're the opposite of that. So metals are malleable and ductile, meaning you can hit them and hammer them into a sheet. You can draw them into a wire. Nonmetals are not. They're brittle. You hit them with a hammer, they're going to shatter into little pieces. Metals are shiny and lustrous. Nonmetals are not. Metals conduct heat and electricity. Nonmetals do not. Metals lose electrons. They become oxidized. Nonmetals do not. They gain electrons. They're reduced. So we can look at trend in metallic character. And so this is talking about how closely do an element's properties match with the ideal properties of a metal. Because with anything, I don't want to go there. Things are not always ideal, right? And yet you still put them into a category. So this one, I think, should be pretty simple. So where is that stair-step line? Well, it's right in here, yeah. And the ones on this side of the line are metals, and the ones on that side are nonmetals. And you can just ask yourself, well, oxygen is over on this side. Is oxygen a metal? I think everybody would get that answer correct. Iron is over here. Is iron a metal? Heck yeah, right? Okay, so if I go down in a period, I'm literally going over here from nonmetals to metals. Guess what? Metallic character is increasing. So phosphorus is more metal-like than nitrogen, even though it's a nonmetal. If we go across aluminum, silicon, phosphorus, sulfur, chlorine, well, we're going from metals to nonmetals. Chlorine is less metallic than phosphorus. Okay? And this is, just showing you those metallic character decreases, metallic character increases. Choose the more metallic element. Let's just do one. Let's do C. Phosphorus or bismuth. So here's phosphorus, and there's bismuth. Well, which one's more metallic? Maybe the one on the other side of the metal line, right? This one's on the metal side, and that one's on the non-metal. So bismuth would be more metallic. This is a summary of periodic trends. Might be useful to refer to. Not going to talk about it.